Welcome to the Explainer. Today we're going to pull back the curtain on a super simple but really powerful rule that basically runs everything, from giant factories all the way down to how you and I are breathing right now. It's this idea of pushback, and it tells us exactly what happens when a system in perfect balance gets, well, pushed.
So, let's start with a little thought experiment. I want you to picture this. You're at the mall, and you decide to walk up the escalator that's going down. You've probably tried this as a kid, right? It's kind of tough.
Now, if you get your walking speed just right, perfectly matching the speed of the stairs going down, you'll notice something funny. You're walking, the escalator is moving, but you're not actually going anywhere. You're stuck in place. Well, believe it or not, that's a perfect picture of what chemists call dynamic equilibrium. It's a state of balance where everything is still happening, but the forward and reverse actions cancel each other out.
So, okay, a system in balance is great, but what if that's not what we want? What if we need the reaction to actually make more of something for us? How do we mess with that perfect balance to get what we're after? How do we take control?
Okay, so this is where it gets really cool. We're about to learn what is basically the cheat code for chemistry. It was all figured out way back in 1884 by a French chemist, Henry Louis Le Châtelier. He gave us a principle that lets us manipulate these systems.
And here's the big idea, more or less in his own words. The most important word on this entire slide is opposes. See, a system in equilibrium doesn't just sit there and take it when you change something. No, it actively fights back. It pushes back to try and undo whatever you just did. It's a true principle of pushback.
So what does that mean for us? It means we have the power of prediction. If we know the system is always going to try and oppose our change, we can know exactly what it's going to do before it does it. We can basically tell it what to do.
All right, so how do we actually use this? Well, it turns out we've got three main levers we can pull to poke the system and get the reaction we want. And those levers are concentration, temperature, and pressure.
First up, and probably the easiest one to wrap your head around, is concentration. This is literally just changing the amount of a substance in the mix. You can either add more of something or take some away. And check this out. The logic is just so simple and elegant. If you dump more of something in, the system pushes back by trying to use it all up. And if you take something out, the system panics and pushes back by trying to make more of it to replace what's missing. It always does the opposite of what you did.
Okay, talk is cheap, right? Let's actually see this pushback happen. Here we've got a reaction that's in a nice, balanced equilibrium. But watch what happens when we disturb it, when we add a little more of one of the starting ingredients. And here's what that pushback looks like on a graph. You see that first big spike? That's us dumping in more reactant. The system immediately reacts. It starts consuming some of what we just added along with the other reactant. And what happens? It starts churning out more product. It finds a new balance, but now it's a balance where we have way more of the stuff we wanted in the first place.
All right, on to our second lever, temperature. The trick here is to think about heat, energy itself, as just another ingredient in the recipe. It's either something the reaction needs or something it makes. So if a reaction needs heat to get going, that's an endothermic reaction. Then adding heat is like adding more fuel. The system shifts to the right to use up that extra heat and make more product. But if the reaction already produces heat, an exothermic one, then adding more heat is like adding a product. The system says, whoa, too much, and shifts to the left to cool things down.
And for our last lever, we're talking about pressure. Now this one's special. It only applies to reactions with gases. And here, we can literally squeeze the system to get what we want.
To get this, all you have to do is count. Seriously. Look at this famous reaction for making ammonia. On the left side, you've got 1 nitrogen and 3 hydrogens. That's 4 molecules of gas. But on the right side, you only have 2 molecules of ammonia. 4 on the left, 2 on the right.
So here's the million-dollar question. If we crank up the pressure, literally squeeze the container, what's the system going to do to fight back and relieve that stress?
It does the only thing it can to make more room. It shifts to the side with fewer molecules. In this case, it shifts to the right, taking 4 gas molecules and squishing them down into 2. It's an incredibly clever trick, and it's how we industrially produce almost all the fertilizer that feeds the world. So, you might be thinking, okay, that's a neat chemistry trick, but this is so much bigger than that. This isn't just theory.
This principle is used every single day to run our world, and it's even happening inside your own body.
Let's look at how we make clean-burning hydrogen fuel. Engineers use this principle like a hack. They set up the reaction, but then they immediately pull one of the products, the carbon monoxide, out of the mix. By constantly removing a product, they never let the system rest. They force it to just keep pushing to the right, making more and more hydrogen. It's genius.
And you don't even have to look at a factory. Just look inside your own body. Your body is an absolute pro at using this. When you take a breath, the huge concentration of oxygen in your lungs puts a stress on the hemoglobin in your blood. This forces the equilibrium to the right, making oxygen lock onto your red blood cells.
And then what happens? That oxygen-rich blood travels out to your muscles and your brain where there's not much oxygen. That lack of oxygen is a new stress. So the equilibrium immediately shifts back to the left, and the hemoglobin lets go of the oxygen, delivering it right where your body needs it most. It's a perfect, non-stop delivery service.
Okay, so we've talked about what works, but it's just as important to know what doesn't work, to bust a few common myths about this.
First up, catalysts. A catalyst is like taking a highway instead of back roads. It gets you to your destination, equilibrium, way faster, but it doesn't change the destination itself. You won't get more product. Next, adding an inert gas, a gas that doesn't react. It's like adding a bunch of people to the audience of a play. The room is more crowded, sure, but it doesn't change what's happening on stage. The system ignores it. Same goes for adding more of a pure solid or liquid.
So I want to leave you with this idea. This principle of pushback, it's not just chemistry, is it? Think about supply and demand in economics, or how an ecosystem responds when you introduce a new predator. This tendency for systems to oppose a disturbance and find a new balance, it's a pattern that shows up everywhere. Once you see it, you start to see it all around you.